It's very hard to project the future, and if you project the future, you're always going to be wrong. It's really just a question of how wrong you're going to be and what kind of guideline your projections can provide to policymakers. Unfortunately, we have to project something. You just can't sort of sit there and speculate. You have to have some more quantitative way to do it. And the way scientists estimate what the climate is going to do is by simulations, computer simulations using relatively complex models of the whole Earth system, which try to estimate what the effect of the greenhouse gases are, what effect that has on atmospheric circulation, how the water balance changes between the ocean and the atmosphere, how the ice balance changes between water and ice, et cetera, with a lot of processes. And we don't understand that system completely. For instance, we can't tell you with high accuracy what would happen to the climate ultimately if you double the amount of carbon dioxide from pre-industrial levels in the atmosphere. The best estimates we have is that the change would be somewhere between 2 and 4.5 degrees Celsius in global average temperature. In some sense, it's a miracle we can even make an estimate that significant. In another sense, it's unfortunate that the mean is 3 degrees, but the upper limit is 50% bigger than that, and the lower limit is 30% smaller than that. We wish we could do better, but we can't. And the reason we can't is because we don't understand the response of clouds to changes in the greenhouse gases. If you think about it, as you warm the Earth's surface, as you warm the ocean surface, you get more evaporation, as I said. What goes up must come down, but in the meantime, before it precipitates out, it forms clouds. And unfortunately, clouds have various behaviors. Low clouds of the type we saw here today tend to have light tops. If you look at them from an airplane above, they're reflecting sunlight. So if you had more of those kinds of clouds, you'd be actually cooling the planet a little bit, or you'd be reducing the warming. It's called a negative feedback. But the wispy cirrus clouds that are ice crystals at 30,000 feet or so, those clouds act like a greenhouse gas. So if we're going to increase those kinds of clouds, we're actually going to have a positive feedback or an amplification of the greenhouse effect. And we don't know how much we're going to increase or decrease by evaporation one or the other type of cloud at what location. It's a very complicated problem. The physics is not well developed. And so we have a range, that's why we have this range of uncertainty of 2 to 4.5 degrees for a doubling of CO2. The other big uncertainty is what are emissions going to do? I don't know. Do you know? Do you know what kind of energy sources you're going to be using over the next 100 years? You or your children, your grandchildren. If you look back today and you try to put yourself in the mind of someone in 1900 trying to estimate what emissions would be today, that person would have to know how many people there would be on Earth, what the energy sources would be. They'd have to know about laptops and airplanes and all this junk we have that actually no one could have guessed. No one did guess. Well, it's the same problem in looking forward. We're just as dumb, I'm sure, about guessing what the future is going to look like in 100 years. But we have to do our best. And what they do is they lock a lot of crazy scientists in the room and they ask them to fight it out. And instead of settling on one answer, the scientists are humble about it. They say, well, there's a whole wide range of emissions in the future we could have from a world where, say, this red curve here, where nobody pays any attention whatsoever to the environmental consequences of anything. We burn up all the oil, coal, and natural gas, and we just don't worry about the consequences. And then we have very high emissions to relatively low emissions where maybe we make a transition to a world which is relatively greener in some sense, where renewable energy dominates, where population stabilizes, and so emissions after going up for a while start to come down, or it could be any place in between. So each of these emissions futures corresponds to a bar here. This is amount of global warming. The reason that there's a bar instead of a point is because of that uncertainty of whether the climate sensitivity is in the 2-degree range or the 4.5-degree range. So that when you put all that information together, you see that future warming could be, if we got lucky on emissions, as low as a little more than 1 degree, although not many people think that we're actually going to make that, to as high as 6.5 degrees, or anything in between. Now, a 1 or 2 degree warming for a place like Australia or the United States might not be so bad. We could adjust to most of the impacts without too much loss. Species would have a hard time because they can't adapt very well. But it wouldn't, I doubt in a 1 degree range that it would be a disaster. Places like sub-Saharan Africa would have greater problems and less ability to deal with it. At 6 degrees, most of my colleagues think that's an out-and-out disaster for everybody. And we don't know whether we get something more in this end or in this end or in between. What we do know is we have no control whatever over the climate sensitivity, but we do have control over emissions. And if you keep emissions down, you can sort of wind up in the lower half of any of these curves, no matter what the climate sensitivity is. So a vigorous policy of reducing emissions could probably keep us somewhere in the 1 to 3 degree warming range. And even that isn't so comforting, because 3 degrees, if the climate is very sensitive, 3 degrees, well, that's a lot of warming to deal with. But that is what I think the aim of policy in general would be, keep us down here. This is the warming that occurred over the last century, significantly less than any of these projections. And this is what the warming would be. It would be pervasive worldwide. In the decade of the 2020s, you'd see a gradual spread of warming in the range of, if you take the central projections that I just gave you, in the range of a degree or so. By the end of of this century, you'd see warming, which particularly at the high latitude would be very large, 6, 7 degrees Celsius or more. That's just a different planet, and we don't know exactly what it would look like. Our ability to project exactly what the consequences are at that high degree of warming are just too limited to take seriously. And you see in this continent, quite a serious warming in the range of 3 to 4 degrees, even in this kind of middle scenario. So, all right, but, and this is a point that I made before, be careful. Not every decade is necessarily going to be warmer than the decade before. The reason for that is there's a lot of jiggling in the climate. So with this band of gray here are projections from a whole bunch of computer simulations of what the climate could do over the next 50 years. In the purple, I've just picked out one computer simulation. Each of these simulations differ by making different assumptions about some of the details of the atmosphere, what the initial temperature would be, et cetera. And we just don't know which is right. But I just point this out to show you that in this particular simulation, while the trend line is clearly up, and it's going to be a lot warmer in 2050 than today, still the decade of the 2010s is a cooling decade, while the decade that we just went through is a warming decade, but then it starts to warm afterwards. So be careful. Any one decade could see some slight cooling. It's small compared to the overall trend, but you will have people going out there, as there are today, saying, aha, global warming isn't happening. Well, it is happening. It's just that it's a long-term phenomenon, not a short-term phenomenon. Now, why do we put any credence in any of these projections at all? Why should you believe me? There are at least 4 lines of evidence which suggest that the computer models we have are actually doing a good job and giving us some plausible representation of what the climate's going to look like in the future. And probably the clearest evidence of that is if you look to the past. So that you could ask, what if we had computer models in 1850 and you knew what the buildup of greenhouse gases was going to be? And how well would they have predicted the last 150 years? And that's exactly what's done here with today's computer models. There are 3 different colors here, if you just bear with me. The blue band is if in one of these computer models you ask it to project Earth's climate over the last 150 years, but without any buildup of greenhouse gases. Let's say there were no industry and no deforestation. The pink curve is what happens if you add in the effect of the human-made buildup of greenhouse gases. And the black line is the actual observed temperature change on each of these continents. And you notice Antarctica is not here because the temperature change, we don't have good projections for Antarctica, so we've left it out. But for the other 6 continents and for the globe as a whole, which is what this is, you will notice that the pink, the simulations that include the greenhouse gas change, has a very good representation of what actually happened, continent by continent, while the blue, which leaves out the greenhouse gases, doesn't reflect what actually happened in the climate, particularly for the last 50 years. That gives us a lot of confidence that the models looking forward will do at least some kind of credible job. There are other pieces of evidence. The pattern of warming one sees geographically across the Earth that's produced in the models actually matches pretty well what's happened. The greenhouse gases have an odd behavior in that they cause the stratosphere to cool even as they're causing the lower atmosphere and the surface to warm. That's what the models say, and that's what we measure using satellite measurements. And we also have direct measurements of how much the sun and volcanoes, two factors which can influence climate change. As the sun can flicker a little bit, volcanoes can add dust to the atmosphere, which can reflect sunlight and have a cooling effect. We know by observation how much these have been causing the climate to flicker, and those changes are much too small to explain this change in temperature. So we have a nice, coherent picture. I want to emphasize, within the uncertainty, that band there is pretty wide. The computers don't go smack on the black curve, but they clearly do a much better job. They clearly generally represent what the problem looks like. Now let me just quickly leaf through a few of the specific impacts that we can expect, some of the highlights, before I talk a little bit about solutions. So I talked about killer heat waves a while ago. Intense heat kills people, and it doesn't have to, but it does, and it's not just, it's a factor in developing countries, it's a factor in industrialized countries. Western Europe had the most outstanding heat wave in the industrial world in 2003, where it's estimated that 35,000 people died from the direct and indirect effects of too much heat. There's the center of the heat wave over eastern France. If you plot out what the history of summer climate has been in that area of Europe over the last 100 years, and then you draw a bell curve to sort of match the frequency of occurrence of various levels of heat, you get something like this. This is the observed climate as it has been. The 2003 summer was way out here, way out in the wings of what the scientists call the wings of the distribution. It was a very unusual event. There's been some simulations which suggest that the likelihood of that event was increased significantly by the buildup of the greenhouse gases already. This is what you get if you take a computer model and ask, well, can we reproduce what the climate should have been over that 100 years? And yeah, we do a pretty good job. The model curve looks a lot like the observed curve. So that means we trust the models up to a point to project the future. Now, if you ask the same models, what will the future look like 100 years from now in Western Europe? If you add the buildup of the greenhouse gases without any future controls, you'll notice the distribution of heat looks like this. And the remarkable thing is that the 2003 summer just looks like the average summer 100 years from now. Now, that won't happen overnight. By the time we get there, people will have more air conditioning. They will be wary of heat waves. The governments presumably will get better at finding people who don't know how to deal with heat and bringing them into heat shelters. But it's a problem. It means that we'll always be playing catch-up. And in this year, what happens when you get the equivalent of the once-in-a-thousand-year summer like we had in 2003? How hot will that summer be? So this is a continuous and building threat that we have to keep our eyes on. Another problem, which is something to keep your eyes on down here, is the drying that's expected to happen at kind of the low to mid-latitudes. This is projections of patterns of precipitation later in this century. The blue areas are areas that will be moister. The brown areas are areas that are expected to be drier. And you notice that the latitude bands of much of Australia, you expect to see a drying, as you do in the southwestern United States and the Mediterranean basin, and some chunks of the developing world which already have some problems with food availability. And the projections are, in fact, that for a warming of about 1 to 3 degrees, food productivity begins to decline in some of these areas that are brown, yellow, or even white to brown. And that's a problem because these are areas where malnutrition and starvation is already endemic in some cases. In the United States, one of the troubling things, and you may have this problem here, population density is increasing rapidly just in the part of the country that's expected to dry out. We don't know where we're going to get the water. Ecosystems are threatened because they have the least species, and ecosystems just don't adapt automatically to climate changes. They're not evolved to deal with such rapid change. This is coral reefs. Coral reefs are very sensitive to warming. You've got the Great Barrier Reef, which is a big, beautiful ecosystem, but very vulnerable to warming. There's been a lot of work done on it. And overall, it's projected that about 30% of species, of all species, become at risk of eventual extinction. 30% of all species become at risk of eventual extinction for a warming somewhere in the range of 1 to 3 degrees. By the way, these coral reefs are also threatened by the ocean acidification, as I mentioned before. Now I'm going to close the impacts part of this by talking a little bit about sea level rise, which I personally do a lot of research on. I'm fascinated with the ice sheets, and I've spent many years studying the sea level rise problem, and I think it ultimately is the most threatening because of its pervasive nature. If you can you see the red on that screen? So the red are the areas, well, let me back up. The current best guess as to where sea level may go in this century is that most scientists who've looked at this carefully think that the increase could be up to about 1 meter. Some think it's more, some think it's less. There's been an argument even within IPCC about this. And the red areas here are the areas that would be completely submerged with 1 meter of sea level rise. So there's quite a lot of land area, although the definition of this slide isn't good enough. It's only suggestive of the actual problem. To be more specific, let's look at a country like Bangladesh, which is probably the worst case, but it is characteristic of a lot of deltaic areas in the developing world. The 1 meter line is here, that is a 1 meter sea level rise would take away, just permanently submerge an area where about 10 million people now live. Wouldn't happen overnight, and the people would try to get out of there, obviously. The purple line would be where 3 meters of sea level rise would take you, and I'll show you later what could bring us 3 meters of sea level rise, and that's about half the population of the country. And the sad thing about Bangladesh, it's a country which has been struggling and sort of clawing its way upward, but it's all almost very close to sea level, and these people have nowhere to go. So if you really did take away a chunk like this, where are they going to go? When they go into India here, even today, people get shot going across the border. This is 150 million people packed into a very small area. It's not clear how they're going to deal with this, and they are struggling now to figure it out. But even in developed countries, we do stupid stuff like this. This is my favorite city in the world, Atlantic City, New Jersey, because it provides perhaps the best example of stupidity of coastal planning. I'm sure you have your own examples here. But, billions of dollars of investment, and look where it is. Man, it's right up on the coast. And what are they going to do if there's 1 meter of sea level rise? I bet they're betting on it right now. They just, they don't know what to do. So, this is a lesson in the failure of intelligent coastal planning, which becomes more and more pointed, that failure, as time goes on and the sea level rises. But the big risk with regard to sea level really comes from engagement of the ice sheets. That 1 meter sea level rise I gave you is for this century. And it assumes that not much of Antarctica or Greenland will be lost. And that's probably a good guess. But the real question is what happens in the years or decades or centuries beyond that? There's equivalent of 5 meters worth of sea level rise in just the western part of Antarctica, called the Western Arctic Ice Sheet. There's about 7 meters of sea level rise equivalent of ice in Greenland, and about 60 meters of sea level rise equivalent in East Antarctica. Now, the good news is that this chunk of ice probably would stay more or less intact unless there were a warming which I think is so big that even the most heedless of governments would long before have acted to stem the problem for other reasons. So I'm not so worried about East Antarctica. I am worried about West Antarctica, which is apparently inherently unstable, at least in places like there's a little area here called the Pine Island Bay region, which is actually disintegrating as we speak here, probably in some way due to the global warming, although we're not sure. And it's been shown in models that for somewhere between a 1 and 4 degree warming, the totality of the Greenland ice sheet simply melts away. So there's an exposure here of 7 plus 5, do the math, 12 meters of potential sea level rise. The question is, A, will that really happen if we really let the warming go on for only a few degrees? And 2, how fast would it happen? So we don't have a good model. We don't have, our intelligence about the physics of ice is very poor, believe it or not, and we are not capable at this point of really projecting what those ice sheets are going to do. So rather than do the same thing we can do with the climate of using a computer model, we have to look to the past and say, well, this is the same curve I showed you before with the CO2 here and the temperature here. All that's different is it's flipped around and the colors are different. So here's today, and we're in a warm period. The last time we were in a warm period, it was actually slightly warmer than today, a couple of degrees Celsius. That's why the peak here is a little higher than today. And here were the CO2 levels. And the reason that even with CO2 only around 300 parts per million, it was warmer, had to do with the orbital inclination, as I explained before. You can ask, okay, when Earth was a couple of degrees warmer, the poles were 3 to 5 degrees warmer then because it's a higher warming at the poles. We know that, again, from the ice cores. 3 to 5 degrees polar warming is about what the middle scenarios show you for the year 2050 or so. What do we know about the sea level back then, 125,000 years ago? Well, and we just published a study on this. Others have studied this as well. It looks like sea level was 6 to 9 meters higher. That means a big chunk of the West Antarctic ice sheet and a big chunk of the Greenland ice sheet weren't there. They were in the ocean instead. But we don't, so, my thinking is that global warming, this is why I believe the number 2 degrees is too much, because a polar warming of 3 to 5 degrees would accompany a global warming of 2 degrees, and that's enough, apparently, to have in the past shoved a lot of that ice into the ocean, melted or destabilized it. But we don't know how fast that would happen. We don't know how many years or decades or even centuries we could sit above 2 degrees and not have it be triggered. We don't know whether if we go up to 2 degrees and then back down, it's too late because we will have triggered it, or we can comfortably sit at 2 or 3 degrees for some time, maybe some decades, and then pull back by reducing emissions and not risk a big sea level rise. What we do know is that eventually, if we cook the Earth that much, we're going to have a humongous sea level rise. So when you put this whole picture together, you can sort of start to understand why the governments all of a sudden have landed on the 2 degree number. This dash curve is this is the warming that's occurred already, the solid curve. The dash curve is sort of a median of all the scenarios if we assume the middle climate sensitivity and the middle amount of emissions. And this curve here is if we don't let Earth get more than 2 degrees warmer than today, and this curve here is if we don't let Earth get more than 2 degrees warmer than pre-industrial times. The governments have been obscure about which they meant when they chose that target at Copenhagen, so I show both. And then these bars are the uncertainty bands for what temperatures the various impacts happen. A lock-in of melting of the ice sheets enough to give, 6 to 9 meters of sea level rise. Risk to endangering 30% of species with extinction. Risk of reduction in crop yields at the low latitudes and areas that can't deal with it effectively. So we see, this is what I referred to at the beginning of the talk. Right here, somewhere in this 2 degree range is where these risks start to build. And there are other ones I could put on this graph if I wanted it to become so complicated that you wouldn't understand it. The point is that below about 2 degrees, the risks seem not zero, but relatively small, but all of a sudden around 2 degrees, they start building. So there is some sense to the policy. Now, if you ask yourself, what would we have to do? And here I'm going to make the transition into the policy world. What would we have to do to avoid that kind of warming? Assuming, that's a preliminary choice. There's a lot more we're going to find out. We could get lucky, by the way. Let me go back here. All these uncertainty bands about where the warming, what damages the warming could have. It could be that the upper ends of these bars are what the reality is, and we could actually let it warm to 3 or 3.5 degrees. I could take a show of hands on how many people want to make that bet. I don't. So, this slightly too complicated graph shows us what kinds of emissions trajectories the globe would have to go through, would have to experience in order to avoid a 2 degree warming. So at this curve down here, the lower end of the blue band, there's a greater than 80% chance of Earth settling down at less than 2 degrees warming. At the upper end of the blue band here, I'm sorry, I think I said that backwards. There's a greater than 80% chance if emissions stay below here of not exceeding 2 degrees. But if emissions go up to here, there's less than half a chance of not busting through the 2 degree ceiling. So somewhere in here, a betting person who is fairly risk-averse, but not entirely risk-averse, would want the world's trajectory of emissions to go. And the key thing to understand here is that emissions globally would have to peak somewhere in the decade of the 2020s, no matter which your risk aversion profile is, whether it's to avoid 80% likelihood of success or less than 50% likelihood of success. And that's going to be damn difficult to do. And the reason is that the developing countries' economies are growing fast, pouring out emissions very fast. It's not apparent how we would turn that around in the course of the next 15 years or so. But the key question we are faced with there is what policies, institutions, international and domestic arrangements, treaties could we institute? What are the general framework which could give us a good chance of either meeting the 2-degree threshold, or if we don't meet it, avoiding sitting above it for very long? And that's what I want to close this talk by discussing at a very general level. What are the policies? This rather grim photo was from New Orleans after Hurricane Katrina, and it underscores the importance of adaptation. It used to be that the developed countries haughtily thought that adaptation to climate change was somebody else's worry. The developing countries were poor, they were going to have the biggest impacts. We're smart, we're rich, we can deal with it. There has been episode after episode of failure to deal with climate extremes in the last 5 or 10 years, which has convinced the developed country governments that adaptation is everybody's problem. It is likely that the industrialized developed countries will try to help. If we're ever going to have an international climate agreement, they're going to have to provide some resources to the developing countries to help them with adaptation. But we're going to have to spend money in Australia and the United States and Europe also on our own adaptation. At the Copenhagen meeting, one of the successes, the recent conference of the parties, one of the major successes was a commitment by the developed countries to shell out substantial amounts of money, $30 billion in the next 3 years, $100 billion over the next 10 years, to facilitate adaptation and emissions reduction in developing countries. We'll see whether they actually pony up the money. They don't have a very good track record of meeting such commitments, but it helps. Even making the commitment and starting the money flow helps making developing countries willing to talk about reducing their own emissions. Again, I'm going to apologize here for a U.S.-centric point of view. I don't have the details on what Australia is doing, although I've been hearing an earful of it this week. These were U.S. proposals. Number 2 thing you want to do is, after you've got an adaptation plan in place, is start capping domestic emissions. In the U.S., these are all the different legislative proposals. This is the emissions as they have been. These are the legislative various proposals to bring emissions down. This is business as usual if the U.S. Senate in its wisdom continues to do absolutely nothing. And the point is, it's a lively legislative debate in the U.S., which has been derailed, at least temporarily, by the economic situation and by our discussion of what to do about health care. But there are proposals ready to go for bringing down emissions, and most of them are based on the domestic emissions trading schemes. I don't want to advertise what Australia should do. Every country will do its own thing and probably do it quite differently. There are a multitude of choices of what to do to control domestic emissions. Emissions trading is one way. Command and control, sort of imposing regulations on energy use is another. Taxes are another. Every country will find its own way to approach it. The third point that needs to be dealt with is perhaps the most important one. It can only be dealt with in the context of an international agreement or set of agreements among several countries, and that's who has to reduce by how much. This is a discussion that's just gotten going. It was also a success of the Copenhagen meeting that for the first time the developing countries were willing to actually put down numbers for how much they would, for their own domestic purposes, be willing to reduce their greenhouse gas emissions. Countries like South Africa, China, India put down credible or at least semi-credible numbers. The reason this discussion is so difficult is here we see the total emissions from China. Well, China just passed the United States as the world's biggest emitter. It can no longer hide out behind the other developing countries. On the other hand, per capita, Chinese emissions are a fourth of what U.S. emissions are, and India's emissions per capita are something like a tenth or maybe even a 20th, I can't remember the exact number, of what U.S. emissions are. And U.S. emissions per capita are about double what European emissions are, and I think Australian emissions per capita are even worse than U.S. emissions. Australia, Canada, the U.S. are the sort of outliers. And again, we see this bar chart I showed you before. Those developing country emissions are increasing. So deciding on what the burden sharing is, what, in the language of the UN Framework Convention, is the common but differentiated responsibility of countries, creating financial institutions like the international emissions trading system that's been proposed and that's been implemented in Europe to facilitate financial flows. This will be a very big part of it. I don't think that there's going to be a mega international agreement, as some people thought would come out of Copenhagen, for some time, but there is going to be cooperation, bilateral agreements between countries on what to do about this problem. I'm not discouraged about that part, but I actually think Copenhagen was a step forward. A fourth part of policy is providing incentives for research and development. This problem is only going to be solved ultimately. Well, let me back it down. We can make progress on this problem, but by becoming more efficient in our use of energy, for instance, driving higher fuel economy cars with existing technology, or implementing more of the cost-effective renewable energy technologies which are starting to become available, like wind power, or exploiting sources of energy that we're familiar with, like nuclear, which don't have any greenhouse gas emissions. There are other problems with nuclear which we can talk about in the question period if you want, but it's an option that some countries are going to pursue, or carbon capture and storage, which is what this plant does, which captures the this plant is not an electric power plant, but the idea, it does bury its carbon dioxide emissions. It's a gas sweetening plant or stripping plant. The idea is to capture the carbon dioxide emissions before they come out the smokestack and bury them underground. We don't know how well that would work or how expensive it would be, but the point is we need research on this. We need research on safer nuclear power. We need research on bringing the cost of solar cells down. Then there's a possibility of actually just sucking the carbon dioxide out of the atmosphere. It's incredibly expensive, but some people, some geniuses think they can do it. I doubt it, at an effective cost, that is. So, there are economic opportunities here for the countries that get out ahead, and, a country like my own has been relatively flat-footed about this. Finally, and this is my penultimate slide, I want to say that I'm actually optimistic about this. And the reason I'm optimistic, although I think we are probably going to temporarily break through that 2-degree limit, is that I think the system, the economic system, the technological system, the industrial system can respond rapidly once the incentives are in place. Once the political leadership is in place and the political will is in place to actually act, changes can come rapidly. And as a micro demonstration of that, I show you U.S. greenhouse gas emissions between 1990, this is a 5-year period, and then it's 1-year periods from 2000 to 2006. Greenhouse gas emissions in the U.S., basically it's this curve, CO2 and total greenhouse gas, didn't do anything. They were flat. This was a period when the U.S. economy grew fairly rapidly at 3% per year. The reason our greenhouse gas emissions didn't grow is because of this spike in energy prices. So with a nice direct incentive, either a cap on emissions or something that raises the effective price of energy, the system responds very quickly. I didn't carry this out further because when you get into 2007 is similar, 2008, the first part of it also similar, pretty flat. When you get to the end of 2008, you have the economic collapse, so the numbers really don't mean anything. But during a period of very robust economic growth, the economy responded, the greenhouse gas system responded, and emissions flattened. That's the way to start solving the problem. Finally, I want to end on both a down note and an up note. The down note is something that President Obama said in his State of the Union address a few weeks ago, but he was talking about health care. He wasn't talking about global warming. Quote, he said, "This is a complex issue, and the longer it is debated, the more skeptical people become." I want you to think about that in light of what's happened in this country, in my own country, in the last few months. There's a burnout factor. But on the other hand, this is not a problem that we're all going to get excited about, pass legislation, then go away and forget about. It's going to require focused attention for years and decades and for the better part of this century, even if we're successful in solving it. We're going to have to live not only with the amount of warming we couldn't avoid, but the process of solving the problem. We will be learning more about the science, learning more about the technology. It's going to evolve gradually. So I think more apt may be John Kennedy's statement in his inaugural address. I love the statement because it's sad but hopeful at the same time. And he says he was referring to a long twilight struggle, year in and year out, rejoicing in hope, patient in tribulation, a struggle against the common enemies of man, tyranny, poverty, disease, and war itself, and I would add global warming. And I think the point of that is his realization, because he was a hard-headed realist, that, you don't wake up one day and all of a sudden the world is a totally happy place. You have to focus, you have to work at it, you have to muddle through. And that ultimately, I think, is how we're going to solve this problem. Thank you.